Hello, and welcome to another lecture in the course. Today we're going to do three sort of big results. Big results with very simple proofs now. So we're going to do Cauchy estimates. They can give us estimates on the sizes of derivatives. I'm going to do Louisville's term, which tells us that, well, we'll get to it. All bounded entire functions are constant. And then we're going to do fundamental term of algebra. Every non-constant polynomial has a root, right? And so this is subsection 3.3.4. All right. So what are the results? So first, Cauchy's estimates, and it's basically we look at the Cauchy integral formula and we do the obvious estimate on, actually you look at the Cauchy formula for the coefficients of the series. So not just for the valued function, but for the coefficients of the power series, and we just do the obvious estimate on the integral and get Cauchy's estimates for the sizes of the coefficients, which are really given in terms of the derivatives. So we're getting estimates on the sizes of the derivatives based on the gonna be like the shape of the domain, how large a disk you can fit in, and the maximum of the value of the function. So you can control derivatives in terms of the value of the function, which is very important and something that really only happens for holomorphic functions. All right. Now, from that, as a sort of immediate application, we're going to prove called Louisville's theorem, which, by the way, is not due to Louisville. Louisville proved a different theorem about different set of functions, not holomorphic functions. This should really be called Cauchy's theorem, but that would be really confusing. So everybody calls it Louisville's theorem because it's sort of the same kind of conclusion as the theorem that Louisville proved, but Louisville proved it about different functions. Yeah. Okay. So what it says is that holomorphic functions which are defined on all of C, on the entire complex plane, and are bounded, well, then they're just constant. There's no way that you can be bounded and defined on the entire complex plane without being constant, if you want to be holomorphic. And Louisville's theorem at once gives the fundamental term of algebra. Right? Just an interesting, maybe sequence of steps, right? But it's a very simple proof once you have Louisville's theorem to show the fundamental term of algebra, which in some sense, the more I think about it, the more it's fundamental term of algebra is really a fundamental term of complex analysis. It really has to do with how complex numbers work. And it gets even more important when you get to several complex variables, for example. So yeah, it's called fundamental term of algebra. And if you look at the MAA monthly, there's a monthly proof, different proof of the fundamental term of algebra. This is a sport of some people is to try to find different proofs of this. A lot of them are actually kind of the same. So there's a few different proofs. This is the complex analysis one, right? And it's actually once we have the tools, it's actually fairly quick, right? So, all right. So first, just a notation to make things simpler. So when we say supreme norm, or sometimes the uniform norm of a function over a set K, and usually the set K is compact, that's why we're saying K. So you write it like this: the norm, the subscript K of F, and we just define it to be the supremum of the modules of F over this set K, right? So that's just the definition. That's to make things simpler, right? All right. So Cauchy Estimates. So if we have some open set, a homomorphic function, and we have a disk, a closed disk that's inside the open set where this function is homomorphic, and we expand F in a power series, right? So we're really interested in is this getting us an estimate on these numbers, Cn, right? So we expand F around P in a power series. We know that that power series is going to converge in a, actually it's going to converge even in a slightly larger disk than R, but it's definitely going to converge in the R disk. So far, you know, that's what we know, right? And then what we get, it's a very quick proof. The proof is essentially as long as the theorem. The size of Cn, right, which is really, you know, just another way of writing this when we did power series. I looked at well, one way to get at the nth coefficient of the power series when we showed that the power series is actually holomorphic, right? We differentiate it, right? And then once you differentiate, you can evaluate, and you can see that that the coefficients are actually have this nice formula in terms of the derivatives of F, right? So you can think of Cauchy's estimate as either estimates on the coefficients of the power series or estimates on the various derivatives of all orders at a point, right? And so what does it say? Well, it says that this number, whichever one you think of it as, is bounded by this expression over here. So it's bounded by the supremum of F on a little circle around P, right? And by maximum principle, now you know that that's the same thing as the supremum over the whole disk, right? But so it's the supremum of F on the little R circle, right, divided by R to the n. Right? So if you can see that it's you get slightly, you know, there's a little bit of a trade-off that you get for this estimate, is how large of a circle can you fit in, the better estimates in terms of the values can you get, right? On the other hand, you know, it's if R gets big, you get sort of more control over here. On the other hand, if you're probably getting further away from P, you're maybe getting less control over here. It's kind of a trade-off. And if you're probably approaching the boundary of your U, maybe then you don't have any control of the top over there. But that's the idea. So that's the so there's a little bit of a, you know, trade-off on the right-hand side. How far away from P, the further away that you can get, the better better estimate you can get, and we'll see that coming up shortly. All right. So another way of thinking about what it just said is that if I stick this R to the n, if I stick it on the other side, I get that this sequence is bounded, right? And it's bounded by the size of F. Now, if you recall from a while ago, we said that a power series converged, right? If and only if these kind of sequences for all r less than the radius of convergence, right? That kind of good stuff. If all those those sequences were bounded, right? So the boundedness of those sequences, of these kind of sequences, is what makes the power series converge. And now we see what the bound is. The bound is actually the size of f on the circle of radius r, right? So that sort of connects it to the development of the power series. All right, so let's prove this. It's fairly simple proof. So we have a formula for Cn, right? This was from the development of the power series. We got this was the formula for this number Cn, right? And so what we do is we just stick the modulus inside the integral. And so when we do that, when the modulus goes inside here, this zeta, that runs over the circle of radius r around p. So the bottom here, when I take the modulus, is just r, right? So I get r n plus 1, right? And on the top, I get the modulus of f, and I'm gonna do, maybe there's really 2 steps over here, right? But I can just replace the modulus of f of zeta as zeta runs over the circle by, something that's definitely bigger, which is the supremum of f over that little circle, right? So that's what I'm doing over here. And of course, don't forget that when you stick the modulus inside, that you're moving from the d zeta to modulus of d zeta. All right. So now let's evaluate this integral, because there is no more zetas, right? The top, yeah, we replaced it by a constant. So that doesn't depend on zeta. The bottom also doesn't depend on zeta. That's a constant, r. So that means that we are just integrating a constant. We're gonna get, or really we just get the length of the circle, which is 2 pi r. And so 2 pi r, the 2 pi cancels this 2 pi, and the r cancels one of these r's. There was an r to the n plus 1, and what's left is r to the n. Yeah, we're done. That's it. Just, this is less than equal to this, and we're done. Now, you could ask, is it possible that this is, we did something sort of, if you think about it, like we did the stupidest possible estimate out here, right? Is it possible that there was that there was something fancier that we could do that would work better, right? In the same set, right? And the answer is no. Unless you know something about f or the domain, or unless you know something else, like with the setup that's given in the theorem, you cannot make a better conclusion. So let's just give an example where the the inequality is an equality, right? So we're saying that something better than this is not possible, right? And you just think of the stupidest possible example, right? So say, well, something. So if you just think of an n, some fixed n, and just think of this function over here. It's just one term, right, in the power series. It's just a polynomial, right? And what you have is that, well, if I take the modulus over here, right, and I look on the circle of radius r, well, this just becomes r to the n. That cancels out the r to the n, and I get m, right? So this is just m, right? Well, we're supposing m is some positive number, right? And well, if I look at Cn, the absolute value of, or just Cn, I mean, it's positive. This is what it is, m over Rn, right? So, yeah, there is an equality, right? This is this side over here, and this is this side over here, yeah. So it's, despite at how sort of, you know, simple-minded that estimate is, it actually is the best one that we can do without extra, you know, extra information. We could, you know, if we had more information, we could do more, right? All right. So let's move to Louisville's theorem. So a holomorphic function that is defined where the domain is all of C, we're going to call an entire function. And if we just say entire, we mean entire holomorphic function. Right? Sometimes the word entire is used for other than just holomorphic function, but so technically we should say, to be completely correct, entire holomorphic function, but we might just say entire. All right. So examples, you know, any polynomial is an entire function. E to the z is an entire function. Sine, cosine, but for example, not 1 over z, right? Because that is not defined at 0, right? So it's supposed to be a complex valued holomorphic function defined on all of z. And it's actually, that's going to be the point of fundamental term of calculus, is that 1 over z is not entire, or something like 1 over z. All right, so Louisville's theorem says that if we have an entire bounded function, then f is constant, right? So if it's entire and bounded, it must be constant. So if it's not constant, it's either not entire or not bounded. All right, so let's prove it. It's really, really simple. Suppose f is entire and bounded, right? So that means suppose it's less than or equal to some m for all z. All right, so let's expand it around the origin. You can expand it around any point, and this formula will actually hold everywhere, right? Because, yeah, I mean, you know, what's the largest disk that you can fit around the origin, right? So we can fit, you know, any disk, right? Meaning this formula holds for all z, right? And f is holomorphic on a disk of arbitrary radius around 0. So we just apply the Cauchy estimates. We say that Cn for any particular n, right, it's going to be less than or equal to the whatever is the bound of f on a disk or circle of radius r divided by r to the n. Well, we know that f is bounded by n, so yeah, so this is n, right? And so we have divided by r to the n, right? So Cn is less than or equal to m over r to the n, and this holds for all positive r, right? Capital M is just one capital M. This holds for all r, and so now you can imagine what's coming next. So letting r go to infinity, because if we're letting r go to infinity, then this thing goes to 0, right? That means that Cn has to be 0. Now, as long as n was not equal to 0, right? If n is 0, then r to the 0 is just 1. It doesn't go to infinity, right? So, but as long as n is 1, 2, 3, 4, well, you know, any natural number, then r to the n goes to infinity, so m over r to the n goes to 0, so therefore Cn must be 0. Well, that just means that that f of z is just the constant term, right? And we saw that this was an equality everywhere, therefore we have that f is constant, right? So yeah, very immediate once you have Cauchy's estimate. And once you can expand around, I mean, you know, we are using a bunch of the machinery already, right? I mean, so okay. Well, now we have Louisville's theorem. All entire bounded functions are constant, and we're going to use it to prove the fundamental theorem of algebra, which is that if I have a non-constant polynomial, then it has a root. Right? And there's sort of other versions of the fundamental theorem of algebra. This is the simplest version of it, right? You can then divide it, and you're gonna get something of degree 1 less, and then you can actually show that up to multiplicity, polynomial has of degree d has d roots and so on, right? So this is the most basic version of it, right? Whenever I have a non-constant polynomial, then it has a root. That means that there is a z such that p of z is 0, right? Some complex number, right? Not necessarily true for real, right? X squared plus 1 as a real polynomial does not have a root, right? But z squared plus 1, yeah, that has I, right? And minus I, right? Right. And this is how we really started the class with, right? I mean, we define complex numbers and we added I to make some polynomial have a root. And what's weird is that once you add I, you get roots of all polynomials automatically. All right. And proof is at this time, insanely simple, which is kind of weird, right? So suppose that that P does not have a root, right? Both for contradiction, right? But I mean, not for contradiction. You can show that it's constant, right? So suppose that it doesn't have a root, right? It's not going to be a constant polynomial. It's either going to be a constant polynomial, but it cannot be. We're going to show that it cannot be a non-constant polynomial, right? So let's suppose that it does not have a root, right? And let's look at if it doesn't have a root, and I can divide by it, right? So I have, let's call it capital R, which is 1 over P, right? And this is going to be an entire holomorphic function, right? So because it's defined at every z and it's clearly holomorphic, right? So now suppose, I mean, if it's constant, R is constant, yeah, there's no contradiction there, right? So let's suppose that it's non-constant, right? If P is non-constant, then the limit as z goes to infinity is in the Riemann sphere sense is infinity, right? And that's not hard to show. It's an exercise earlier in the book. It's basically this idea that, I mean, if I have a polynomial of degree d, then sufficiently far out, it really sort of, you can bound its value from below by some, some number times z to the d, right? And then you can show that z to the d goes to infinity, right? So you can, because it's going to behave far enough away from the origin, it's going to behave like z to the d, and you can see that that's going to infinity, right? So as long as d is bigger or equal to 1, right? As long as it's non-constant. So we have this this statement over here. The polynomial goes to infinity. That means R has to go to 0, right? Because it's 1 over P. So that goes to 0, right? Well, I mean, if something goes to 0 at infinity, that means it's bounded, right? I mean, it can do something, maybe, near the origin does something, but then it just dies away. So, I mean, it's clearly going to attain some maximum, right? So it's going to be bounded. Well, if R is bounded, it's an entire holomorphic function which is bounded. Louisville says that it must be constant. Well, if R is constant, P is constant. But that was a contradiction here, right? So we were assuming that it's non-constant, right? Oh, So that's it, right? It's ridiculously simple. All right. So now that we've, we proved the fundamental term of algebra by analysis, right? So what are those algebras doing, right? Who knows? Well, some of my best friends are algebraists, so they must be doing something. All right. So next time, what we're gonna look at, we're gonna move to defining holomorphic functions via integrals. So we really already, kind of been doing with the Cauchy formula, but maybe you can, you can talk about doing this more generally, defining if we have, some function, if we integrate it against a kernel, which is holomorphic in the added variable, we get a holomorphic function. This is a common way of constructing holomorphic functions. And sort of, in some sense, like a very special case of it is the Cauchy formula, but it comes up in many more applications. So that's what we're gonna do next time. So see you then.